All right, so today we're going to be talking about chapter 17. It's going to be section 4, and it's about solubility equilibria. But here I put molarity solubility because the concentration is a lot more focused on the actual KSP values. And the theory is something that you can not sort of gloss over, but yeah, you can sort of gloss over it. So it's good to know, it's good to keep in mind, but you'll be able to recognize when they come up. So right here, we have another K constant, and it says the solubility product constant is the product of the concentration of ions, each raised to their respective coefficient power. That's a mouthful, but it's just what we've been doing all semester, where K values are going to be the products or the reactants, and here I put these exponents, and these are signifying the coefficients that they're raised to. So you'll see how we use them just in a bit. And as always, solids and liquids are not going to be in this equation. So it's just going to be pure aqueous equations. So as with K values, the higher it is, that's going to mean that the solid or what you're examining is going to be a lot more soluble. And only solids have KSP values because only solids are the ones that can, well, become a solute, right? You can't have an aqueous solution that becomes a solute. Well, you can, like, this can be technically used for salts, but it's gonna have its limitations at some point, right? And something that we know is that solubility will change based off of the pH of the solution that you're adding it to and the concentrations of other ions. Now, this part right here, it's going to be incredibly important because once we see the common ion effect come up here, we're going to see that this is it's going to take a toll. And what we can infer is that the KSP values they're not going to be constant if the solution is not constant itself, right? So let's try an example really quick. It's no new math, so everything that we've learned so far is leading up to this. So this example, it says solid silver chromate is added to pure water and some remains undissolved. Okay, so we can maybe infer that it's not going to be very soluble. Let's keep going. The silver ion concentration is 1.3 times 10 to the negative 4 molars. Assume that silver chromate is saturated and there are no important equilibria involving Ag plus or chromate 2 minus. And the question is obviously to find KSP. So let's analyze this problem first. It gives us a silver ion concentration, but it doesn't give us a silver chromate. So that's something we can write off to the side. That the concentration of Ag plus is going to be equal to 1.3 times 10 to the negative 4 molars. All right, is there anything else? Some remains undissolved, added to pure water, but water is not going to be in the equation because it's a liquid, so we don't need to know that. And yeah, I guess that's it. So now we need to find an equation for what this is saying. So if we write down that we have silver chromate, and it's a solid at this point, and it's going into water, let's see, this is H2O, it's going to dissolve into its ions. Ag plus, it's going to become aqueous, and chromate 2 minus, also aqueous. However, something I do notice is this isn't, what's it called? Balanced. Because right here we have 2 silver ions, right here we only have 1, and we only have 1 chromate ion. So it's going to be pretty easy to balance it. We have 1 here, we have 2, and we have 1. So there we got our equation. So from this, we can actually find the concentration of this chromate ion because we have the concentration of the silver ion. So if we put it this way, that the concentration of the silver take off this M so that we can write everything in moles. And we want to convert this into a concentration of chromate. Well, we have a relationship right here where it's a 2-to-1 ratio. So something we can do is say we want to cancel out these 2 moles of silver, so that for every 2 moles of silver, we're going to have 1 mole of chromate. So it's essentially multiplying by 1/2, right? Because this is going to be half the concentration of silver. And let's see what we get with this. We have 1.3 times 10 to the negative 4 times 1/2. And we get 6.5 times 10 to the negative 5 molars. So that's the concentration of our chromate ions. So why do we want this? Well, we want this because our KSP formula is the products over the reactants. But remember, silver chromate, this is a solid, so we don't really need to worry about it. So we're only gonna have these 2 concentrations. So first we have 1.3 times 10 to the negative 4 molars of silver. And we have 6.5 times 10 to the negative 5 molars of chromate. Are we missing something here? Yes. We're missing our coefficient exponents. So silver ions, this has an exponent of 2 because it comes from here, and this one will have an exponent of 1. So let's calculate this. We're going to have 1.3 times 10 to the negative 4 squared multiplied by 6.5 times 10 to the negative 5. And we get that our KSP value is 1.09 times 10 to the negative 12. One significant figure, so 2 significant figures, I mean, from these two. So it's 1.1 times 10 to the negative 12. And no units because it's a K value. So that's our answer. All right, so this is a continuation of the video that we had before. It's chapter 17, section 4, about our KSP values, but right now we're gonna be doing kind of a different KSP value. It's something we have not gone over in this course, but it's still good to know just in case any curveballs are thrown at you, or to understand it conceptually. So right here it says that the KSP for calcium fluoride is 3.9 times 10 to the negative 11. And it's asking us to calculate the solubility of calcium fluoride in grams per liter. So the KSP is already given to us, so we can actually write that down. The KSP for calcium fluoride is equal to 3.9 times 10 to the negative 11. Now, this is an incomplete formula. So in order to know what our exponents are going to be, we should write down the formula for its equilibrium. So we say that calcium fluoride is going to dissolve into its calcium 2+ ions and its fluoride ions. So this isn't balanced because on this side of the equation we have 2 fluorides, in this side we only have 1. So we can just put here that 2, and yeah, it's pretty balanced. So now we know that the concentration of fluoride is going to be 2. Well, have an exponent of 2. So something we can do now is we can make an ice table. Making this ice table is going to help us know the change that it's going to undergo. So we have I put this ice table on the wrong side. It's supposed to be right here. Ice table. So this is going to be the same because it's the same solute in the water, and also it's a solid, so we don't really need to know it. we only care about these two. So first, they start at 0 because you're putting this in an empty beaker, so both are at 0. And eventually it starts dissolving, so this one dissolves into its single one and into its single ion. This one dissolves into 2 ions, so that's plus 2x because it's in terms of their concentration. So at equilibrium we have x and 2x. So now that we know the concentrations of calcium and fluoride, we can plug this back into our equation. So we can say that KSP is equal to the concentration of calcium, which is x, times the concentration of fluoride, which is 2x, and this one is going to be squared. So, and that's going to be equal to 3.9 times 10 to the negative 11. So 2x squared, 2x times 2x is 4x. So we have 4x squared times x, and that's 3.9 times 10 to the negative 11. This is just 4x cubed. We need to divide both sides by 4 because all we're trying to do is we're trying to find this x. So if we have 3.9 times 10 to the negative 11 divided by 4, we get that x cubed is equal to 9.75 times 10 to the negative 12. And now what we need to do is we need to take the cube root of x in order to cancel out this this exponent, and that should give us our answer. So at the end, x will be 9.75 times 10 to the negative 12 to the power of 1/3. Remember, when you're doing radicals, having an exponent to a fraction is going to be equal to having the nth root of that factor. Like if we have something to the power of 1 to the 5th, that's the same as taking the 5th root of that something. Just a little side note. So right here we've gotten that the cube root of 9.75 times 10 to the negative 12 is going to be 2.1 times 10 to the negative 4. And that should be our answer. So this is what we got for x, and remember that this is in moles per liter. So the original question is saying to calculate the solubility of calcium fluoride in grams per liter. So now we just need to convert this, and this is going to be relatively easy. We have 2.1 times 10 to the negative 4 moles, and that's going to be per liter. And now we just need to convert this into our moles of calcium fluoride. So taking a look at the mass, I don't have my periodic table out. Excuse me. So here we're gonna have 1 calcium and 2 fluorides. So that's gonna be equal to 40.078 plus 2 times 18.998. I'll add the 4 in. And our weight in grams is, let's just say about 78.1 grams of calcium fluoride. So multiplying this out, we get that this number times this number is 0.016 grams per liter. And we can just say this is 1.6 times 10 to the negative 2 grams per liter, and that's our answer. And remember, this is in terms of grams of calcium fluoride per liter. So yeah, that'll be it.